All right, welcome to Images and Compressions here at Alfred State Intro to Web. All right, so part of the reason why we got to go over things like this is because students pull images offline and they don't really look at how big these images are. And regarding performance of the web, this is probably the biggest factor and one of the easiest ways to crush the performance of that website. So, and this is also going to start putting me into my little tropes and what I say over and over and over again, very much like a broken record, is content is king. All right? No doubt about that. If you don't have the content, you don't have a website, period. Performance is queen, okay? Generally speaking, and this is one of the things where if you're not trained in how data is collected and how to actually read performance metrics and data analytics and going down that route, if you don't actually know how to read those things, you can easily look at a chart and go, well, consumer reports are saying that, performance of the website is like the 5th on the list, or content is 4th on the list. I can guarantee you that if the website doesn't load very fast and you don't have the right content, those shoot to the top of the list. The reason why they are low is because websites, generally speaking, the ones you interact with on a daily basis, have the thing you want and perform well. There's a reason why Amazon doesn't look good. It performs good. It has the thing you want. Amazon, right? There's an excellent example. Now, one of the things I also want to do is a little demonstration here. So the next slide is going to be filled with text. I'm going to challenge you to read as much as you possibly can until the text fades away. Okay. What color was the coffee mug? Okay. What color was this person's eyes? Okay. Where were they? All right. How about now? So images are powerful, and they're powerful because they are processed about 60,000 times faster than text. If you want to communicate something, you do it through an image. Now, sometimes this can be difficult, but images are powerful, all right? Most of the web is images, and it's images for a reason, because you can communicate something quickly. You don't have to write it, and people aren't going to read. I promise you, people are not going to read. And we'll get into different motivations later in the course, but generally speaking, just assume that no one's going to read. That's a good place to start, all right? 50% of the world is still on 2G. All right, this is a problem. Now, this is a problem if you are trying to address emerging markets, because these people are going to have things like feature phones. Look, a premium experience for them is going to be like Pixel 2, let alone a feature phone. Okay, and just to highlight what this means is 1 megabyte on 2G is 8 seconds. Okay, that is massive. That's a massive amount of time. Okay. So the primary questions that we really need to ask ourselves here is, okay, what are we talking about? We're talking about images and compressions. Why? Well, it's because you need to know the tools that you have exposed to you, how you use them, which we'll go over that here in a second, and then where, what tools, and when. When do we use these? Okay, those are the questions that we're trying to ask and then properly answer immediately after. So we got to go abstractions layer first. We got to talk about color spaces, okay? And the reason why we got to talk about color spaces is because it highlights the difference between a mathematical representation of color, like we do with computers and what you're used to, and what is perceived. And we'll show that here in a second. But I really want to highlight the little triangles here off to the left. Now, sRGB is what we're going to use for this class and has traditionally been the color standard for the web for a long time. Rec 2020 is right around the corner. Give that a couple more years and we'll be talking about Rec 2020 in the color space that represents. But if we're going to highlight sRGB, we're talking about this right here. So this triangle right here. Okay, so what this little color space thing and this little like lazy triangle thing with a green, rounded green up top here is the perceivable color of humans. And notice that Rec 2020 gets very, very close to that green. However, what I do have to point out is people are very, very, very bad at distinguishing colors. Okay, generally speaking, they'll be able to tell the difference between fundamentally different colors, like this aqua color here and this actual true green over here, or red and yellow, right? People can tell the difference between those. But if you're talking about this green versus this green, people aren't going to be able to tell the difference. And this is kind of what Rec 2020 is trying to accomplish here. It's like, okay, we have a color space that goes as far as what people can reasonably perceive. Okay, awesome. Now we got that. How are we going to implement it? Okay, well, first thing that we need to understand is how light interacts with each other. So traditionally, you can get, well, this is true. You can get any color you want using 3 colors of light: green, blue, and red. This is fundamentally different from physical color, like paint. We will not be talking about paint. So 3 light colors. I want to point out this. Right here in the middle, white, green, blue, and red. If you mix all 3 of those together, you get white. Ta-da! Color space. Okay, so and this is going to send me on my little rant about computers in general. Computers in general. Anything that we have that is a computer, a monitor, anything that we consider technology is a representation of reality through the series of ones and zeros. Color spaces is no different. Okay, so how do we represent 521 Newton meters? No, it'd be nanometers of light. How do we represent that? Okay, well, we do that through color space. We say, okay, this huge chunk of zeros and ones represents this wavelength of green. All right. This also brings me into, okay, awesome. We have a mathematical representation of color, a very precise algorithm. Awesome. No. All right, this brings us into the difference between perceived and mathematical representations of color. Okay, so up to this point, we have color spaces, which mathematically represented. Up here, sRGB. This is what we're used to, okay? This is what sRGB looks like, mathematically represented. I want to bring your attention down here to perception and highlight some pretty big differences. Here's this red for sRGB, and here's perception. Red sRGB, the perception of that same value. That's pretty orange. Okay, now one of the arguments is, okay, well, this really doesn't matter. We'll just over-represent that color. So if we really want to show red in the sRGB scale, well, I'll just add more red. Well, the problem is you run out of red very, very quickly. So there are new color standards coming out, like Rec 2020, that is perception-based. And what this perception is going to do is say, okay, well, you're going to give me a number, and we're going to convert this mathematical representation of it into the perceived or the the perceived value of what you're trying to go for. And what this ends up looking like is that we have a much more gradient, smoother transition between colors. Because if you've noticed, in perception here, we got orange and then almost immediate drop off. Green, immediate drop off. Violet, will be more of this one. Violet, immediate drop off. When you come up to sRGB, this red has a much smoother gradient. This green has a much smoother gradient. This violet here has almost none. And perception is the exact opposite. It's almost double the size. Okay, so we got some weird things going on in terms of what people are perceiving. And if you're wondering why, part of the reason why is that these colors mean something out in the wild. If you see something that's orange, don't touch it. Right? If it moves and it's a frog and it's orange, or it's a snake and it's orange, don't touch it. Right? We're designed to see things that have threat. However, we also are designed to see things that have value. So if we're talking about traditional human history, the value of an orange is incredible because that's fruit and is dense in calories and nutrition and all around good. Okay? You want to be able to see the orange. You want to be able to see the apple. You want to be able to see, if I bring you over here, the grape or the blueberry or the blackberry. You want to be able to see those things. And there's a reason why our perception of those colors has a bigger tolerance to it. Okay, same thing with blue. Blue is, water and sky. All right. Now, with that said, I am not on a very good monitor here, and I can almost guarantee you, if I went to my better monitor, I can pull out more color differences. But the orange is the big one, the green is the big one, and the violet is the big one. Those are the ones that are the most dramatic. So if you happen to be on a color accurate monitor, you're going to be able to see more than I can. All right. So this brings up delta E. Since we're talking about monitors, monitors are only so accurate when displaying color. And in general, from a marketing standpoint, from a business standpoint, people that make monitors, unless you're in the professional market, color accuracy doesn't matter. It just doesn't. The reason for that is because most people can't tell the difference between color anyways. So if they can't tell the difference between color anyways, well, you can save a buck by not color calibrating. And companies have also discovered, and I call it the Best Buy effect, because people don't see color very well and they don't necessarily care about color accuracy, they care more about vivid colors than anything else. So that TV that you see at Best Buy is not color accurate. I can almost guarantee you. Okay, so be careful about that. So talking about color accuracy and what people can actually see or not, how many of you noticed immediately this little ominous circle right here? Yeah, most people do. How many of you actually noticed this randomly generated color over here? The amount of difference that's here is significant compared to this. This is like 10 bits on the sRGB scale. This is almost 50% different. And this is randomly generated color. This is highlighting the difference between your ability to distinguish color and your ability to distinguish contrast. All right? Big difference. Okay, sRGB, been talking about it a lot. It's 8-bit color, 16.7 million possible colors, all right? And most of your monitors are sRGB. This is what you're going to be targeting in this course. Later on, we'll talk about Rec 2020, and by later on, I mean 2, 3, 5 years from now. All right, image types, two major ones. There's rasterized and vector. Rasterized is what you're used to. Vector is SVG. And we'll get into the differences here in just a second. Rasterized, good for most images. Okay. Features and functions depends on the encoding. So this is where your differences in like JPEG or PNG, Webp, VIF, JPEG XL. Oh, what else is out there? GIF or GIF, depending on who you're talking to. All right. Those are where those differences come from. So how you implement these compression algorithms and these features, that's the differences between the file types. Compression types, you have lossy and lossless, and vectors, but they're not really compressed. Okay, so we'll talk about lossy. Lossy, they use approximate data, removes data based on guesses. Okay, this data compression is irreversible. So once you compress this, once you go from a raw file type, a raw image, and then you convert it into a JPEG, that's it. That image is gone. Now I recommend you make a copy, but you're not going to be able to take that whatever was converted and go back to raw. It doesn't work that way. Okay. This type of compression is not very good at sharp edges and small details, which we'll get into the reason why that is here in a couple seconds. DCT, discrete cosine transform. This was the original compression algorithm. 1974 it was made. It's been around for a long time. All right. It works by discarding high frequency small components. So, and this is part of the reason why that sharp edges have such a hard time, because okay, yeah, it's going to blunt those sharp edges. And by sharp edges, I'm not talking about this, and there's a reason why I picked this image. I'm not talking about this. This is going to be okay. I'm talking about grass, right? Talking about stuff like this. So this area right here just got crushed with this compression. Yeah, just the nature of the beast, right? A raw image is obviously going to represent the image accurately, but this comes down to perception versus reality. Okay, so I can perceive this difference, right? I really can't perceive a difference here. I might be able to if I had the image side by side, but not having that image side by side, I can't tell the difference, right? I can down here. That got crushed. Okay. HEIF, high efficiency image file format. So this is your newer codecs, and it works very similarly to DCT, but what it does is takes big blocks and then essentially just represents that into a table. So if you have a big blue sky with no clouds in it, that's going to default to a 64 by 64 pixel block, and then that will be mathematically represented in that table. So pixel 1, which would be the actual RGB value, and then from the rest of the pixels is going to be just refer to that RGB value. So that's how you save a bunch of data that way. All right. So this was using one of the high compression formats. Can you tell me which image is the compressed or the original? Give you a couple of seconds. So if you answered that the left is the original, you are correct. Now, if you want a little bit of a cheat code when you're starting to look at compression image, you can start looking for anti-aliasing over here. Okay, so this is going to have that jagged look when you compress it down. And then light is another big one up here. So this light is really smudged and blown out. Not true over here. And then there is very, very little noise over here in terms of anti-aliasing. And then you can also pick out more details. So this is like anti-pigeon stuff right up here. It's possible it's fire prevention too, but probably not. Okay. I also want to point out the difference. So this is a 5 megabyte photo. Ridiculous. Okay. And then we can compress that down to 267 kilobytes. And it looks like this. And you're not going to notice these little details like over here when the actual image is shrunk down on the website itself. So saving a lot of data here, and we're getting a lot of performance with no loss. So yay. Okay. So now this one is much easier to point out in terms of which one's compressed. Original image, definitely not original image. Okay. And the reason why this one struggles so much is because there's so much detail in this grass over here that it's just it's gonna crash it, period. Okay. So there's that. And here is a little example of how this is working. So you can represent any image by using any combination of these blocks. All right. You can represent any image with a combination of those blocks. So what this video is going to do is demonstrate that that is true. So I'm going to skip here because they're talking. Oh, they beat me to it. So here's their little example going through here, and then they're going to drag their phases down. Now notice that these are all the same blocks from the last page. Over here is going to be the one that changes. This is the original image. So as he changes the phase, notice that he's down to 1 now. So it's just a gray block. And as he goes up, this gets closer and closer to the original image. And you're going to get into about here where it makes sense. And then all the way over, you get the original image. So as he was dragging this phase back up, you were adding in these images to make that original one. Now, this is the same example twice, except for with a real image now. So he's going to click on this little 64 by 64 block. All right, awesome. No, I'm going to pause here. Notice that there's a bunch of zeros in here. So this is referencing, this one. This 0 is equivalent to this. Okay. So all these zeros, this is where you save data too. So all these zeros are referencing this little block right here. Okay. So as we move the quality up or down on this, now moving quality down means we're going to save more data, but we're also going to ruin the image itself. So now he stopped right about here, which makes sense to me because this image is very close to this image and we saved a bunch of data. Now, if we go more down, which I'm pretty sure this video does, this is just going to get obliterated. And this is what happened in that other image when I was showing you with the grass, where if you go too far down, the image gets crushed. So if I play this now, this is where this compression algorithm doesn't do a very good job because as soon as you go down even a little bit, this nice round edge with a high contrast background is going to get blurry almost immediately. So this is an example where it just doesn't work out very well. Okay, so that is the end of that little video there. Let's continue on. Lossless. Okay, so lossless, if you need to compress an image and you want the flexibility to be able to undo whatever compression that you're trying to do. So PNG jumps to mind on this, but largely speaking, I would much rather have a copy of that original image and store it somewhere, and then just compress down whatever image that you're trying to do. Compress as much as you can. And then if you go too far, well, you just go back to that original image and compress it less, right? Okay, so lossless it works by guessing the next pixel. So literally go in order by the table that these pixels are in and essentially just guess at what the next pixel color is going to be. So this is not very good at large color changes. So anything that's sparkly, not going to be very good at, and many colors, which again, sparkly is not going to be very good at. So probably the worst case scenario is like bedazzled dresses where you have a bunch of like fake jewels, and they even worse if they make their own color. Just not good, and not good at all. Fireworks is another one where not a good one. So if you're taking fireworks, 4th of July type of thing, having a lossless compression is not going to be good for that photo. You're going to want to use something else. And this is a little bit of a rant more than anything else, but this image, take a look at it. Which one is the original image? Which one is the new one? The new compressed one. Okay. So I'm assuming you guys have picked up on the fact that the left one is always the original image and the right one is always the compressed one, except for this one's not compressed at all. So we changed the compression from lossy to lossless, and it got bigger, a lot bigger, almost 300%. So be very, very careful about which tool that you use, right? So if you're coming from a raw image type, which holds every single pixel in the image, which makes for a very big pixel, or not big pixel, but big image. Yeah, you can go lossless and you're going to save some data, but you could save a lot more data by going lossy. SVG, not technically compressed. It is a file type based on a series of points and then mathematically generating new points as it gets bigger or smaller. So SVGs can be very, very, very small. The problem is the more complex the image is, like we're looking at now, it's going to be very, very, very large in terms of what it's trying to do, because it has to represent all those points somehow. Now, SVG is very good for simple logos, and that's about it. Anything else, don't use SVG. Yeah, and the example that I'm about to show you here is that this image is not very complex. It's about 1/3 off to the left, a little bit of line, okay, and you got nothing off to the right. And it went from 123 KB to 6.7 megabytes by converting this into an SVG. So by simple image, I really mean simple image, like a logo. Okay, and even complex logo like the Burger King logo that we showed you last time, that's pushing it. Okay, even that might be too big. JPEG, one of the originals. Okay, it's lossy, good for old browsers because it's been around for a long time, supported by everything. And you get two types of encoders. You get baseline. Okay. So baseline is what you're used to. If you just click JPEG on any type of image manipulation software, you're going to get JPEG. And then you have, and let's back up a little bit. When you load this in, if you don't have a very quick internet connection, you're going to load this image in line by line, full resolution. Progressive, well, it fixes that problem. It's going to load in a low resolution version of that image and then progressive, render over it until it's full resolution, okay? And I'm going to show you the difference between those two. So here's baseline. Notice that I have a 2G network. I'm trying to download 1.6 megabytes worth of an image. Okay. And notice over here is how long it's actually taking to download that. We're up to 16 seconds, 21 seconds, 27 seconds. Okay, just to spoil the ending here, this video is 2 minutes and 20 seconds long. In internet world, you could have read War and Peace before this loads. Okay, no good, not good at all. So this is where JPEG Progressive comes in, and this fixes that, well, reasonably fixes that problem. The real solution to this is make your images smaller. But okay, cool, we got a blurry image. At least we got something. All right, 5, 4, 3, there we go. About half rendered to something usable. And I would consider that usable at this point. Now, notice that this video is still 2 minutes long. So this is a usable image. This is still trying to download, but it's usable. It's good. It gets the point across. All right. Pretty good tool to have, especially if you are using older browsers like an IE, or you have to target older browsers like an IE. This is useful. PNG, lossless. So PNGs tend to be pretty big because of the lossless nature. It is the other OG of the file formats for images. Okay, so again, if you're targeting IE and not a modern browser, you're going to be limited to JPEG and PNG. And the reason why you'd use PNG over JPEG is because of the alpha support. So an alpha channel is your invisible layer, either in front of or behind the image, depending on how you have that configured. Okay, Adam7 is interlacing, so another progressive loading type. The problem with this one is it adds a lot more data to the file itself, so it makes it about 20% bigger. And on top of it, it looks like garbage. So let's go ahead and show you how much garbage we're talking about. So here's normal PNG. Oh, did I replay this? Nope. So let's go over here. That was 5 seconds in. Okay, so this is going to go line by line again. Also notice that this is 2 minutes or a 2 minute long. So that's going to take forever. Let's go to the... All right, so if we're talking about Adam7 now, the interlacing, we're going to go ahead and hit this video here. Okay. Here we go, here we go. We got a blurry image now. And what this is going to do is it's going to render down and then across, down and across, down and across. So you're going to get this absolutely awful looking image. And it's going to look awful for, well, a long time. I'm going to let this go for a while just to demonstrate what I mean. Still loading. Still looks awful. It's trying. Okay, so I think I highlighted my point here enough. This is the tools, not rules problem. Okay, so this is generally speaking, I would consider this a bad choice if you're using interlacing PNG for progressive loading. If you need progressive loading and you have to target an older browser, then I would use JPEG. If you, for some reason, absolutely have to have an alpha channel and you absolutely have to have interlacing, well, and you absolutely have to target Internet Explorer, yeah, this is your only option, but you should be rifling through everything else before you choose this. Okay, so Webp. This is generally the choice for encoding. Okay, so you get a bunch of options here. You get lossless and lossy. You can choose what you want here. Alpha channel support, metadata, and progressive loading. So now the only thing I don't like about Webp is the progressive loading aspect of it. Yeah, and the example that I have coming up doesn't even support it. So you do have to go in and add progressive loading yourself, but at least it has it, okay? So if I come over here, we got 2G, we have 750 kilobytes worth of data. We're gonna go ahead and hit play on this. Going. Okay, so we got a bar. Very barsy. Okay, it's going. Now, notice this is still on 2G. Notice that the file size itself is much smaller. And this is still taking a while. So, generally speaking, now to be clear, I can get this image size much smaller. And I do mean a lot smaller, like 30 KB. Because this would compress really well. So the answer here, especially if you're targeting second and emerging markets, okay, you need to be very aware of this experience, because if they're on 2G, are you going to expect them to wait 30 seconds for an image to load? I wouldn't. It's ridiculous. GIF or GIF, depending on who you're talking to, okay? I'm going to cover it because I'm going to tell you not to use it. The only time that you should be using this is if you're trying to make a meme. That's it. Moving on. AVIF. Okay. Lossy. Okay. So we're doing pretty good there. Based on a video encodec or codecs. Okay. Also kind of interesting. So it just takes the first frame. So if you didn't know, videos are just a series of images. So how many images per second? So this is where you get your FPS number from. And then, but it doesn't have progressive loading, and it does, however, the trade-off is it does better regarding edges. And the image that I have here really highlights what I'm trying to show with compression. I went way too far on this image, way too far. But it's usable. So if you guys don't know what this is, and I don't know why you would unless you've been here, this is the Ohio State Library. So there's about, I think it was 10 floors of just nothing but books like this, just over and over and over and over and over. Right there's floor 6. We are missing all kinds of detail. Like this floor has reflection. These books have more detail. Like the only time you actually see reflection is down here under the stairs, because it's just crushing all the color around it. So this is what images look like when you take it too far. But once again, once you get this down into a reasonable size, you're not going to see these differences. This brings up the perception versus reality problem again. It's like, okay, well, what do people actually perceive and notice? If the answer is they don't, and you can save a bunch of data and you can make your website faster, they'll notice that the website's faster. But if they're not going to notice that the image is better, well, that's a win-win. Take away all the data in the image and make the website faster. Obviously, okay? So when you start talking to designers, when they start going, well, no, I want my images the best they possibly can be, you need to start showing them that, hey, no one notices. Right? Okay, so this brings us to the end of the presentation here, and there's a couple things I want you to take away from it. You're new in codecs, you should be using Webp or AVIF. Okay, if you're targeting modern browsers, then yeah, go ahead and use them, and you're going to be okay. I like Webp. Webp is easier to work with. Use GIMP or Photoshop for batch processing. So if you have I think I had 100 images on the last design project that I had. Yeah, don't do that by hand. No, let the computer do that. And then you get the benefit as well as making everything consistent, where everything is 500 by 300, something like that. Okay, use a website or technically a progressive web app, so it's still a website, called Squoosh. And it's made by Google, and what this website does is allows you to drop in an image, it compresses it for you, and then you can actually drag between what compressed looks like and not compressed looks like, and then you can fine tune to the point where you like for that image. And then once you have those settings, so it'd be quality of say like 23, and then resolution of say 720p. Once you're good with that, then you can go, okay, cool, let's throw that into GIMP or Photoshop for batch processing, and then you just make all your images that setting. Okay. And the biggest thing I want you guys taking away from this is tools, not rules. Every single one of these codecs has its place. Okay. And then every single one of these codecs and image files has its no, what were you doing with that in this play or under this use case? All right, be very aware where these things, are. Let's back up a little bit. Each image codec is designed to do a particular thing. Can you use it for something else? Sure, but there's probably already a tool that was designed for that use case that you're trying to attempt. Let's put it like that. And then the last thing I want to point out is that I compressed all these images that you've seen on all these slides, which was 35 of them, I think. And I saved 132 megabytes. This is how much difference that you can have. And none of you looked at it except for the ones that I intentionally crushed and went, oh, well, yeah, that's a terrible photo. And the one you're looking at right now is a good example of that. This is a really nice photo. It's been compressed, significantly compressed. All right. So with that said, that is the end of this little presentation here. And I will see you guys in the next one, which I believe is HTML. So we're going to actually be doing some legitimate work now. See you then.